Hi, linear algebra students. So in this video, we will make a proof of one of the properties of the cross product, which is, by the way, the hardest to prove. It is this one. U cross V is equal to 0 if and only if U and V are parallel. Okay? And to do that, we're going to refer to the definition, right? So just let's rewrite the definition. And I'm going to write that in blue anyway. So definition, okay? Remember that U cross V, okay, is the vector. It has to, well, U and V must be in R3 themselves. They must have three components. But the definition will be to take the determinant. And actually, let's write them in this notation. It's actually better. And then you have like U1, U2, V1, V2. Okay, then the negative of U1, U3, V1, V3. Okay, and finally the determinant of U1. Oh shoot! Okay, I messed up the first component. Let's actually go back and fix it. There you go. So the first component is not that. I just realized that it's the third component. So what we have here instead is U2, U3, V2, V3. There you go. So remember that to prove this thing, we are referring to the definition of the cross product. Okay? So actually, there's one part of the proof that is easy, and it's the if part. So let's do that part first. Okay? So we are supposing that U and V are parallel, and we will prove that the cross product is 0. So if U and V are parallel, then it means that V is a scalar multiple of U. So V is equal to K times U for some K, for some constant K being a real number. And it means that we can actually write out V in terms of U quite easily. So V will be K U1, K U2, and K U3. Okay? Let's actually write that in green because obviously what I'm going to do next is I'm going to plug this in my cross product formula. Okay? So we have here K U1, K U2, and K U3. Okay, and from there, that's it. We replace in here. So U cross V will be equal to, and now we just write the determinants. Okay, so U2, U3. But now every time I hit V's, I replace by these components, right? KU2, KU3. And then same thing over here, right? So the negative, like U1, U3. Then you have like KV1, KV3. And then finally, you have U1, U2. And there you go. You have like KV1, KU1. I messed up all of these now. Okay, so KU1, KU3, KU1, KU2. And I'm gonna go fast here just because I think you see what's happening. What's happening is that in all of these determinants, the second row is a multiple of the first. Like, so in other words, all of these determinants are 0. So let's actually write that down to complete the proof. So all of these determinants are 0, okay, since the second row is a multiple of the first. So since the second row is a multiple of the first. Okay? since it's of each of them, by the way. So of each. Okay. So as you can see, this proves the if part. So QED for this part right here. So now it remains to prove this part, which is, I think, harder, but let's actually try it and see if it's really harder. So I'm going to erase just this part. I'm going to keep the theorem and the definition. Now we're doing the opposite. We suppose that the cross product is 0, and we want to prove this. Okay? So, okay, let's go like this. Okay, if you cross V is 0, cross V is equal to the 0 vector, it means that all of these 3 determinants are 0, right? All 3 determinants are zeros. Okay? And from there, what we want to do is we want to prove that the second row must be a scalar multiple of the first. Okay? So, all right, what can we say from this? Okay, so all 3 determinants are 0. Okay. Oh yes. Okay, I know what to do. So what does it mean? It means that all these matrices are not invertible. Okay, and let's give them names. So let's call like A2, 3. So let A2, 3 be equal to U2, U3, V2, V3. Okay, and then we're gonna give similar names to A1, 3, which is the matrix in the middle. So U1, U3, V1, V3. And A1, 2, which is the matrix that is like right here, U1, U2, V1, V2. Okay? Now, all of these matrices are not invertible. Okay? All these matrices are not invertible. And what we're going to do is we're going to use the invertible matrix theorem a couple of times. Okay, so first of all, the first thing we can say out of the invertible matrix theorem, I think it's statement L, but in any case, so A2, 3 transpose, and actually let's write them down. It will be very useful, right? So U2, U3, V2, V3, okay? Then A1, 3 transpose, okay, which is U1, U3, V1, V3, and A1, 2 transpose, which is equal to, there you go, U1, U2, V1, V2, okay? Well, these are also non-invertible, and this is what we want to say by the invertible matrix theorem. So are also non-invertible. Invertible. Now let's use the invertible matrix theorem again, but now on the transposes, okay? What does it mean? It means that the columns of these matrices are linearly dependent. So the column of these 3 matrices, right? A2, 3 transpose, A1, 3 transpose, and A1, 2 transpose are linearly dependent. Okay. However, since each of these matrices have only 2 columns, it means that these columns are also scalar multiples. So let's also write that down. Since these matrices have 2 columns only, matrices have 2 columns, then they are scalar multiples. Okay, so from there I need to erase, I can erase my definition now, and I can also erase this part. I will keep the transposes. So there we go. So what did we find out of this? Well, look at the columns, okay? We have that, okay, so the vector u2, u3 will be equal to k1 times the vector v2, v3. Okay, and we can say the same for the other 2 matrices, okay? We can say the same for u1, u3 will be equal to some vector k2, v1, v3. And finally, again, the same for the matrix that we have right here, u1, u2 must be equal some k3, v1, v2. Okay, and for now, nothing guarantees that K1, K2, K3 are the same, right? Like this is going to be true for some K1, K2, K3 in R. But now what we will do is we will prove that these constants must actually be the same, okay? So how do we do that? Very simple. Let's label these equations. Let's label this like equation 1, label this equation 2, label this equation 3. Okay? So, for example, let's go like component by component. From equation 1, we get that U2 is equal to K1 V2. Okay? However, from equation 2, okay, you get that, oh no, it's equation 3. I messed up again. There you go. Sorry about that. From equation 3, you get that U2 is equal to K3 V2. Okay? So as you can see, this proves that K1 is equal to K3. We will use the same argument to prove that K1 is equal to K2. Look, from equation 1, we get that, so let's read the second component now. We have U3 is equal to K1 V3, but from the second equation 2, we get that U3 is equal to K2 V3, okay? So this means that K1 is equal to K2. So putting this all together, and let's actually erase this argument now. We don't need it anymore. Okay. So now with this, what we can conclude is that K1 equals K2 equals K3. So let's call them just K, right? Okay, what does it prove? Well, we can make a vector with U1, U2, U3, okay? So what it proves is that U, which is now the vector U1, U2, U3, will be equal to K U1 from KV1 from equation 2, let's say. Then it's going to be equal to KV2 from equation 1, KV2 from equation 1. There you go. And now finally, k v3 from equation 1 again, let's say. Okay, which is equal, obviously, k times v1, v2, v3, which is equal k times v. And as you can see, we're done. Okay, so for some k in real, and this means by definition that the vectors u and v are parallel. So u and v are parallel. So now, as you can see, we proved the second part. So QED for this part. So as you can see, this proof is harder than the first proof. So if they're parallel, quite easy to prove that the cross product is 0, like from straight out using the formula. But this part, notice that we had to use the invertible theorem twice, and we also had to use the argument that if these are all scalar multiples, then it turns out that the scalar multiple must be the same. Okay, so that's the idea of the proof. Hopefully this helped. So see you either in class or in the next video.